a, right here it's 0, let's say, and then do this for each order of derivative, and then assemble them together, use them to manufacture the coefficients, and that is a Taylor series. So for example, in this case, you get something like this. And then remember, keep the big picture in mind. This says that if e to the x, which wasn't discussed in the previous section, right? And now you ask, is this just like 1 over 1 minus x? Is it true that this is just like 1 over 1 minus x, which can be written as a sum of power series? And this new big theorem says that, well, I don't know yet, but if there is such a series, then it has to be that one. If that one doesn't work, then no one else will work. And so then there's two issues. The first of all, you look at this and ask when it converges. What is the radius convergence? In this case, the radius convergence is infinity, so it converges everywhere. But that's just first question. The second question, okay, now it converges no matter what x is, but that doesn't mean that it converges to this one. So the tougher question to ask is that, okay, this one converges for OX. For each x, you sum it, you get a sum. What exactly that sum? Is that really e to the x? That's the second question. And for that, we have this remainder, some theorem about remainder. And that remainder, as you recall, is, it says that this one is less than equal to what? n plus 1 factorial. X minus a n plus 1. Right? So look at known last time. And that is the thing that you have to rely on. This is the bound of that remainder. And so that means that it's a difference between a partial sum that's on the right-hand side and the left-hand side. And that discrepancy is called a remainder. So if you can show that discrepancy gets smaller and smaller as you retain more and more terms, that essentially says that that series converges to the left-hand side. So proving that it converges to the left-hand side is the same as proving that the remainder goes to 0. And therefore, this estimate of the remainder, the size of the remainder, becomes very useful. So if you use this, last time we showed that indeed, not only is this convergent, but it actually honestly converges to this guy. So very good news. All right? And then what I said I was going to do today is to show you a lot of examples and show you practical ways of doing things. All right? And show you practically what you shouldn't do. All right? So sine x is, remember I said that this is 3 o'clock in the morning, you're awakened, you have to immediately recite. I'm serious. All right, this one. All right, this is this. N goes from 0 to infinity, n factorial, x to the nth power, where 0 factorial is defined as what? 1. 1 factorial is also 1. 2 factorial is 1 times 2. 3 factorial is 1 times 2 times 3, and so on. Right? As before. And so then 3 o'clock in the morning you're awake and you immediately recite this. And then you're allowed 1 minute, to write down this one. This one only you see that sine is an odd function. Remember that? So it's not a surprise that you see that you only have odd power term. Third power, fifth power, seventh power, okay, and so on. And the list of these results are in page 762. And just like cosine, this one is equally important. This one is even function. So if you find a power series centered at 0, which that is to say what is called the Maclaurin series. Taylor series centered at 0 is called Maclaurin series. So its Maclaurin series would have only even power terms. 1 minus x squared 2 factorial plus x 4's power 4 factorial minus x 6 power 6 factorial plus, and so on. You see that alternating only even power term, and then resembling the terms in e to the x. And then these three are new in this section, whereas previously in the last section we already talked about this guy. That was before we even talked about Taylor series. Is that right? Why? Because this guy somehow has somehow is a cousin of 1 over 1 minus x somehow, right? Why is this so? Because on the side you see that the derivative of that guy is 1 plus x squared, and this therefore can be think of as 1 over 1 minus negative x squared, and therefore is 1 minus x geometric series like this, alternating, right? And so if then you take the derivative back, right? Because that guy you take derivative here, then you integrate it back, then you'll get back that one. And then the big theory in last section is that you can do it term by term, right? And so if I do it term by term, the first one becomes x. Next one is x cubed over 3. Next one is plus x 5th power over 5 minus x 7th power over 7 plus dot dot dot. And then normally as you integrate back, you should have should worry about the constant term, right? Which there's an integration constant. But here you know that when x is equal to 0, arctangent is 0, and therefore left has to equal to balance right. So right hand side you see all these are 0, and that has to be equal to 0. The constant term has to be 0 as well. So that one is sort of old. We learned that in the previous section. This one is also old. Last section we dealt with this already, right? As you recall, and let me erase that one. This time let me write it over here. 1 plus x. I know that 1 over 1 minus x is 1 plus x squared plus x cubed plus dot dot dot. This one you replace x by negative x. Then you get 1 minus x plus x squared alternating minus x third plus x fourth minus dot dot dot. Right? Okay? And then if I take antiderivative, what is that? Isn't that an antiderivative? And therefore, right hand side I take term by term antiderivative. So x minus what? X squared over 2, right? Plus x third power over 3 minus x fourth power. Let me line things up more nicely. X minus x squared over 2 plus x third power over 3 minus x fourth power over 4 plus x fifth power over 5, right, minus dot dot dot. And that's the next result here. So start with x, and once again, because you integrate from here to here, term by term, once again you have to worry about the constant term, the zeroth order term, the constant term, which has to be 0. If you look at the left hand side, that constant has to be 0. So there's no constant term. So this one is x minus x squared over 2 plus x third power over 3 minus x fourth power over 4 plus dot dot dot. All right. So you see that this is alternating, this is alternating, this is alternating, this is alternating, but all these have the same parity. This is all odd power term. This is all odd power. This one all odd power, right? And this one doesn't have factorial. This one doesn't have factorial, but this one includes both even and odd power terms. There's no missing terms here, right? Except the constant term. So these two we learn before we even learn Taylor series. But it will be instructive if I just take this as an example and then show you explicitly, that if you were to take the definition of Taylor series, constructed term by term, you do get that one. Just to reinforce the definition that we introduced last time. So let's say f of x defined as ln 1 plus x. Then what is f prime of x? Wouldn't that be 1 over 1 plus x? And what is f double prime of x? Wouldn't that be, this is what power of 1 plus x? Negative 1. Is that right? So if you take the derivative, so you get negative 1, and then power drop by 1. So that's squared. Is that right? And then chain rule, 1 plus x, taking derivative with respect to x, that's 1. So there's no extra factor from chain rule. F triple prime of x, what is that? You have negative 2 power here. So as you pull out negative 2 power, it becomes positive 2. Right? And then 1 plus x cubed. Take derivative again, 4 derivative of x. That would be, well, this one's negative 3, right, power. And therefore, you have, as you take derivative, you have negative 3 factor. Along with 2, wouldn't that be negative 6? But I'm not going to write it as negative 6. I'm going to write it at negative 3 factorial. That's much nicer. Right? And so 1 plus x, 4th power. And therefore, I go back here to, I begin to see the pattern. And therefore, I go back here, rather than writing 2, I'm going to write as what? 2 factorial. Rather than writing 1, I'm going to write 1 factorial. Even this one, I can, if I want, I can write 0 factorial. Right? Okay, but I'm not going to do that. X, f to the 5th power, just check one more time. Negative 4 power, right? So negative 4, multiply that, and then alternating, and therefore this is what? 4 factorial. 1 plus x to the 5th power. And begin to see the pattern, right? Now therefore, f prime of 0, f of 0 is what? F of 0 is 0. F prime of 0 is, plug in 0, that's 1. F double prime of 0, plug in 0, that's negative 1 factorial. F triple prime 0, what is that? That's positive 2 factorial. F 4th derivative at 0, that's negative 3 factorial. 5th derivative at 0, that's positive 4 factorial. Alright? And then, what else do I need? I have to take f of 0, and that's f of 0 is still f of 0. F prime of 0 is still f prime of 0. What I have in mind is that in the Taylor series, the coefficients of the first order term has f prime of 0 over what? 1 factorial. Is that right? So what is that? 1. And then f double prime of 0 supposedly divided by what? 2 factorial. And therefore that becomes negative 1 over 2. This one, if you were to take triple derivative of f at 0, which is 2 factorial, then you're supposed to divide by 3 factorial. Wouldn't that give you positive 1/3? Are you with me? What is 2 factorial? This one is 2 factorial divided by 3 factorial. That's the extra factor. Is that right? Extra factor of 3. Cancel out, you get 1/3. This one, it's f 4th derivative at 0. That's negative 3 factorial already. You're supposed to divide by 4 factorial, right? So it's negative, and it's 3 factorial divided by 4 factorial is 1 over 4. And likewise, f 5th derivative at 0 divided by 5 factorial, that must be positive 1 over 5. And so now the pattern, is very clear. It's alternating, and it's all 1 over something. And that's consistent with this. Right? Okay? It's consistent with this one.